So I think these, obviously they build on concepts that we've talked about before, but they represent a deviation from the kind of force, electric field, potential energy, potential kind of story that we've been building up. These are kind of using the results from there, but kind of ignoring the path that we walk to get them. And as such, the questions are a little bit more simplified and a little bit more straightforward. And I think you guys will find when you're doing these problems, it's a lot more just simply finding a single equation that you need that fits the format and the style of the question, and going from there. It's a lot less manipulation, in my opinion, and having to put 3 and 4 equations together. So hopefully that'll be something that you guys find makes your life a little easier. Okay, so the first question is here on the screen. It says that we can use capacitance to measure fuel levels. So this is a real-world application. We're told to consider 2 parallel plates, and we kind of, as we read this, there's the schematic over here on the right. 2 parallel plates, they have length L and height capital H. They're immersed, at least partially, in some jet fuel up to a depth of lowercase h. So that's here you can kind of, this cartoon for waves or whatever represents the top of the fuel level. And we're told that the dielectric constant of jet fuel is 1.7. It's not mentioned, but we assume always that the dielectric constant of air is 1. So we're told that the capacitance for the portion of the plates with the air gap adds to the capacitance for the portion of the plates with the fuel gap, and that gives the total capacitance. And all that's really saying is that you can treat these like capacitors in parallel, and when you have capacitors in parallel, you can just directly add the capacitance from each. So we're told what the plate separation is. This is the variable lowercase d right here. And we're asked to find what is the change in total capacitance if the fuel level drops by some amount, 1 centimeter. So the first thing we need is the capacitance of a parallel plate capacitor. So that's equal to epsilon naught times the area divided by the separation between the plates. So I think that's, and I guess if we want to write out exactly what's going on with this statement about the total capacitance, we'll call this parallel plate. We'll make sure to label everything nicely. This I shouldn't denote is in air or vacuum, because these have a dielectric constant that we assume to be 1. The same thing for a parallel plate that isn't in vacuum. We have the dielectric constant out front, but otherwise it's the exact same. And this is with some sort of dielectric in the middle. So what we want to kind of figure out is what is the total capacitance. I'm just going to call that capital C. We know that this has contributions from I'm going to call this script A. That's the capacitance from the parallel plates that are kind of sandwiching the air gap. And C subscript F, which is the corresponding part here. It's on either side of the fuel gap. So each of these is a parallel plate. We can write down what the capacitance is for each. And I'm going to use A subscript A to denote this is the area of the capacitor in the air region. Write down the dielectric constant because fuel is a dielectric. There's some area of that capacitor submerged in fuel, but the distance is still d. So this is our total capacitance here. And now we just want to work with this so we can factor out some terms, simplify it a bit, and get it written in terms of the provided variables. So specifically, we want to break down the area into the heights and the length of the capacitor. So we can factor out epsilon naught over d from both terms, put the rest in square braces. The area is is, what were we given? We're given capital L here. That's the length. So we're thinking about the planar dimensions of this plate. We have length and we have width. I believe we have width, don't we? Oh, sorry, we have height. I spaced out there for a second. We have these heights, we don't have width. So our capacitor looks something like this. We looked on from the side. We have length, we have height, and here we have distance. Okay, so the area in the air gap is L times capital H minus lowercase h. The area of the capacitor in the fuel region is just L times lowercase h. So we can factor out an L from both these terms and simplify it a bit further into terms with capital H's and terms with lowercase h's. So we have H plus kappa minus 1 times lowercase h. So this is our expression for the capacitance in terms of kind of all the variables given. It might seem like we're done, but if we revisit what the question was asking, it was asking us to figure out what is the change in capacitance if we have a change in the fuel level. So this change in the fuel level actually means that we want to figure out what delta C is, given that we have some delta H is minus 1 centimeter. So the way that I'm going to do this is a few ways. Some of them are increasingly complex but give simplified answers. I think the easiest way to do this is we will define an initial condition. So we'll say that in the initial condition, let's say that the fuel level, the height of the fuel is at H, and in some second condition, it's all the way down to 0. And for the case of our question here, we'll set H to 1 centimeter in a minute, but I just want to solve it in terms of variables so that we can get kind of a flexible solution if perhaps 1 centimeter wasn't the answer. Or sorry, we wanted to think about 5 centimeters, 10 centimeters, that kind of thing. So what was the capacitance in the initial state? Well, we can just copy what we have. Kappa minus 1. And we could write H initial. But because we said H initial, I'm just going to give that the variable H, switching the meaning of what H is. But that's the initial capacitance in the initial state when the fuel level is higher, when the fuel level is fallen. Our final capacitance will be, we have the same prefactor out here. We still have capital H, but now we've said that the final H, this guy right here, it's going to be 0. So that term goes away. And now what we want is just what is the difference, right? So what is the change in total capacitance? It's the final minus the initial. And what I think we're left with is minus epsilon over L, or sorry, epsilon L over D times kappa minus 1 times H. So the way that we've defined this, H is a positive quantity, so if you wanted to solve this and actually get a number for this problem, you would plug in positive 1 centimeter here, right? If you think back, if you re-listen to the way that we've described the problem, H is where the initial fuel level was, and it went down to 0. So we want to have a 1 centimeter decrease. Say this started at 1 and went down to 0. But nevertheless, if you plug into here, I think that'll give us the answer we need if you want to actually get a number from it. Okay, so second question, also on capacitors. Yeah, so John had a question here. He said, can we explain the LH? Oh, you might be misreading my handwriting. So let me tidy that up and then that's an H. This is also an H. So this H minus H is just simply this here. So it's the height of the air region. So it's probably just a handwriting issue. Yeah, so this is also an H. My H's, I guess, I think my L's are pretty regularly L's, right angles more or less. My H's tend to perhaps resemble L's a little bit, but hopefully it's clear. All right, so question 2, we're told that the concept of dielectric strength of a material is the maximum electric field that it can endure before the electric forces cause it to break down. So basically what this means is you have, um, this typically applies to an insulator or a dielectric, but basically you have bound electrons around the nuclei of atoms, but the electric forces get so high that those electrons want to get pulled in one direction, the nuclei want to go in the other, and the whole thing rips itself apart. Okay, so let's just call this, we'll give it a name or a variable. So dielectric strength, because it's the maximum electric field that a material can endure, I'm going to call it Emax. Okay, so we're told that nylon has a dielectric strength of 14 megavolts per meter. Nylon fills the space between the parallel plates of a parallel plate capacitor. We're told that the nylon breaks down when the potential difference between plates is 5.7 kilovolts. The plates have an area of 84.5 centimeters squared, and we're asked to find the maximum charge that the plates will hold when the nylon is removed and we have air. So this question is deceptively simple, and I think it's a good example of one that you want to read carefully and think carefully about, because I think at least half the information in here is somewhat useless, or I don't want to say misleading, but it's just not necessary to solve the problem. So I think what the question in terms of the misleading information or the not useful information, I think what we are trying to, the path they're trying to lead you down is that we can obtain the voltage by integrating the electric field. And if we're at a case where we have parallel plates, the electric field in here is constant, so we don't even need this integral. This just becomes V is equal to E times D, where D is this separation. And if we're at the limit, where we are at the maximum electric field before whatever material, you can imagine that in our case here, we're told we have nylon, so imagine that we have kind of a slab of nylon in here. So we're told we're at the maximum limit, or at the electric field where the nylon breaks down. So there's a corresponding potential. Apparently it's 5.7. It's the maximum voltage for this nylon. So I've used max subscript to denote this is the maximum voltage, and I've done an N as well just to denote this is for nylon. So that's equal to the dielectric strength for the nylon times the distance between the plates. So what this tells us straight away, or you might think is a useful piece of information that we're getting that wasn't provided up here, right? We have the area, but we don't have the distance between the plates. You might think, okay, good. We found an expression or an equation for the distance between the plates. And next, we want to consider what's happening with the air. We're told what is the maximum charge the plates will hold One is removed and we have air, and we're told what the dielectric strength of air is. So remember, if you have these parallel plates, they work like a capacitor. So we want to find the maximum charge. So if you have something that has capacitance, the charge on the object is equal to the capacitance times the potential difference across it, or just the V. You could write delta V as well if you want. So for a parallel plate, this is not sigma, this is epsilon naught, because now we have air. So I'm ignoring the fact that we might have a kappa in front. We don't need that because we have air. So epsilon naught A over D, that's the capacitance, that's C. And then we have V. Well, we actually want V max in this case for air, because we want to know what the maximum charge is. So yeah, even at this point, it looks like, okay, we are going to need this D right here. The one thing you come to realize is that if we work with this for a little bit, the second term, the maximum voltage, can be related to the dielectric strength, which is actually a number that we have. So V is equal to E times D. These two D cross off, and now we can just figure out what the maximum charge is. We have a constant, the permittivity of free space. We have the area, which we were given, it's 84.5 centimeters. And we have the dielectric strength of air. And we, in fact, if you examine this result, we didn't need D, and we didn't need anything to do with any nylon. So that's kind of, I guess, just more a test of your critical thinking and having faith that you can reach a simple answer without actually needing anything to do with this nylon. Just have faith in what you know. And to make it clear, just so there's not another writing problem, that A is part of the subscript. So this is the maximum breakdown electric field, or the dielectric strength as it's called here. This is the 3 megavolts per meter. That quantity, that's the last term there. Okay. So this question is not about capacitance. This one is on resistors and the topic of resistivity. So we have a carbon film resistor, we're told, and again, this is like another real world application. This is not a made up kind of structure, it's a real device. So we have a carbon film resistor. We're told that it's made by depositing a layer of carbon in kind of a thin film onto an insulating ceramic substrate. So that's kind of what's denoted here. You can notice there's a carbon wrap, and it's on this transparent ceramic center. So once this carbon layer is down, it's kind of all over this ceramic substrate, and a helix is etched from the carbon, and you create a long resistive path. So we cut out kind of the regions that are in the middle here to leave a long spiral behind, because that allows it to be very, very long relative to the length of the cylinder. So we're told to consider a carbon film resistor. It's a 1/2 meter long path, and it ends up kind of this width right here. I guess it's labeled down here as well. That ends up being 2 millimeters. We're told the total resistance for this resistor, so this whole resistor here is basically, you can imagine it from A to B. This is the resistance R, and this resistor here is modeling this whole thing right here. That resistor has a resistance of 100 ohms. We're told what the resistivity of the carbon film is, and we're asked to find if this path has a rectangular cross-section, calculate the thickness of the carbon layer. So the idea of this is, imagine that this spiral was fully unwound. It would look something like this. It has a rectangular cross-section. It's very long. Has dimensions L, W, and T for thickness. And this is what we're trying to find, is the thickness. So again, if I'm being completely honest with you guys, everything here about how this is assembled, it's kind of for your interest, and it's so like it's not misleading, but it's just not necessary for solving the problem. So being able to digest this information, but realize that it's not, there isn't a critical detail in here in terms of getting to the answer. That's good reading comprehension. So if we have something of a particular resistance, we can solve for that resistance by multiplying the resistivity times the length divided by the area. So the resistivity is a property of the material. The resistance is a property of the material and the geometry. So this area here in the denominator, this is the area, the cross-sectional area that's perpendicular to the direction of current flow. So in our model here that we're kind of extracting from this whole cylindrical situation, the current flows through this strip. Here's our strip here, so the current, maybe I'll change. The current is flowing kind of through this face. And because it's a rectangle, the area of that is really, really simple. The resistance is equal to rho L divided by the width times the thickness. What we want to solve for is the thickness. So we just need to bring the T over to the left side and the R over to the right side. So we have the resistivity times the length divided by the resistance, also divided by the width. So this is our final answer. Super duper simple. There's really nothing more to it than that. Like I said, I think you guys will find that most of these questions, at least they're not 3 pages of algebra and stuff like that. So that's hopefully a relief. Okay, so this is our last question for tonight. I guess this one will end up being pretty short. Again, a function of how these questions are a little more simple. So we've got a current flowing between 2 metal plates, which are partially submerged in a solution containing sodium and chlorine ions. We're told these are from table salt, for whatever that's worth, and it's shown in this schematic on the right. There's a 5-volt battery connected to the plates that's driving current through this wire here, and then also through the solution. So each plate has an area of 250 centimeters squared, and this is just the area that's submerged here. And we're told what the separation is, it's 5 centimeters. And here's kind of the key details are the ones that we'll have to work with carefully. Every second, there are 2.6 times 10 to the 16 sodium ions, which have a positive charge. These reach the negatively charged plate, and that's denoted here with this arrow. And similarly, we have 3.92 times 10 to the 16 chloride ions, which have a negative charge. Those reach the positively charged plate. That movement here is the bottom arrow. And with all this information, we're asked to calculate the resistivity of the ionic solution. So really what this boils down to is we need to kind of parse this information here about the movement of ions. We need to translate that into a current. We have a voltage. So if we have a current, we have a voltage, we can leverage Ohm's law to figure out something about the resistance, and then from the resistance, we can work to find the resistivity. That's going to be the kind of process that we go through. But the more challenging aspect and really the biggest part of this is figuring out what's going on with the current. So in the solution, we have a total current, which I'm just going to call capital I. That's going to be equal to some contribution. Actually, I don't want to write this out yet. We just want to find out what that is. And there's a contribution being carried by the sodium ions. There's a contribution being carried by the chloride ions. So the chlorides are negative, the sodium ions are positive, and the key thing that we want to remember is convention says that current is positive. So even though that current comes about from the movement of electrons, when we're doing the physics, when we're doing kind of all the drawings and the schematics and stuff like that, we assume that it's kind of flow of positive charges. So when you have a battery, the big plate is the positive one, the little plate is a negative one. I've drawn the current coming out of the positive one. That follows that convention that I just mentioned. So let's first deal with converting these quantities we have here into units that we can actually deal with and we want. So let's first work with the sodium ions. We're told that there are 2.68 times 10 to the 16 sodium ions per second reaching the charge plate. So what I'm going to do is multiply this by a couple conversion factors and get this into a more useful unit. So the first thing that we want is we have sodium ions. I think it should be clear, but in terms of being very careful with the units and the math and stuff, we can't do anything with sodium ions as a unit, but there is one missing electron per sodium ion. That's what gives it the positive charge. So I have one, I'm using E, that's our unit of elementary charge, or the charge on an electron. I've just put a positive here. This is kind of similar to the charge carried by a proton. This positive here is just kind of a placekeeper for us. We of course know that there are 1.602 times 10 to the minus 19 coulombs in a given kind of quanta of one elementary charge. That's how many coulombs it is. So at this point, if we kind of look at where we're at, these will cross off, these will cross off. And in terms of the units that we're left with coulombs per second. That is going to leave us with the unit amperes, which is the unit of current. So I'm not going to do this calculation. I'll leave it up to you guys if you want to do it. But what I'm going to do is I'm going to call this number that results when we put this into a calculator. I'm going to call this I'm just going to call this INA. And this is just the magnitude of the current. This is greater than 0. And we'll keep that and do something with it in a second. So we'll repeat the process with the numbers we had for the chloride ions. Got a bit more reaching the positive plate. So we have 3.92 times 10 to the 16 chloride ions per second. There's one excess electron per chloride ion. There's minus 1.602 times 10 to the minus 19 coulombs per excess electron. And this is going to give us minus what I'm calling ICL. So this is the current. This is kind of the magnitude of the current carried by the chloride ions. This is just kind of like a scalar, and I'm leaving the minus out front to tell us that it's a negative charge carrier. So let's think briefly. Let's look at what's going on here in terms of the arrows, the way the sodiums and the chlorine are going. And this helps us. We want to figure out what the total current is, because some of the current's being carried by positive charges, some of the current's carried by negative charges. This is kind of unique to ionic currents. Normally, like I said, we're familiar with electrons and solids and stuff like that carrying the current. So we want to be able to add these together and figure out what the net current is. So what I'm going to introduce is the idea of a current vector. So this I is our total current. It's equal to the vector current carried by the sodium plus the vector current carried by the chlorides. So we're going to write down a vector for whatever this the current is carried by the sodium. It's a positive charge carrier. It has a magnitude INA, which was what we use over here. And based on the arrow we have in our diagram, it's pointing to the right, so that goes in the positive I hat direction. We can do the same thing for the current carried by the chlorine. It's pointing to the left here. This is minus I hat for the chloride. And now we see that these minuses multiply together, they'll give us pluses. We can drop the vector notation because the vector notation really just told us if we should add or subtract. And we can say that the total current is just the sum of the two kind of magnitudes that we found above. So remember, I said that ICL is positive, negative is hanging out, but that's independent of this ICL variable being positive, INA also positive. So when you convert the rate at which the ions are hitting the plates, convert that to amps, at that point you can just add the positive quantities up together and you will get the current. And from there we're basically done. I think we have room to finish up on the side here. If you have something that is exhibiting a resistance, that can be attributed to a resistivity and current passing through a certain cross-sectional area over a certain distance. So we have A and we have B from the details of the problem. We're looking for the resistivity. We don't know what R is, but we have the fact that this is powered by a 5-volt battery and there's a certain current flowing. So Ohm's law says that V is equal to IR, or conversely, R is equal to V over I. You can sub that in here. What we're left with is V over I is equal to rho A over D. We want to solve for rho equals the voltage of the battery, which is 5 volts, the separation between the two plates, which was 5 centimeters, divided by the current, which you would have figured out over here, divided by the area, which is provided, that's 250 square centimeters. So this is our answer for that one. So I think that's all I have for you guys tonight. I hope you found these questions kind of were as simple as I claimed they were. I can stay around for a few minutes and answer some questions, but if not, we can all go enjoy the early finish on this one. Yeah, John has a question. Go ahead. You can't find the resistivity in Professor DeVet's notes. That's very interesting. I would expect that to be I would have expected you to have seen that. Maybe I'm just half a lecture ahead or something of where you are. So I can give you a quick explanation, and maybe if time permits, I'm gonna actually go pull up what you guys have on the site. Maybe there's enough time here. So maybe you just haven't gotten here yet, but the resistivity, let's break it down into different pieces. That's rho. It's a material property. It's basically a statement on how tightly bound the electrons are in a material, how much like the crystal structure of a solid, for instance, how resistive is it to flowing the electrons through, how tightly bound are any electron passing by, how much are they affected by kind of the nuclei in there. Something like a metal that's a really good conductor, like copper or gold, has a very low resistivity. Something that is a poor conductor, like a ceramic, would have a huge resistivity. Even a poor conducting metal like aluminum has a much higher resistivity. So that's the first piece that goes into this. The next is kind of this length here. If we're just using this bar that we had drawn previously of this film as a resistor. The idea behind the length is the further that the current has to travel, the harder it's going to be. That's basically the gist of it. Um, so I don't know if you guys would have talked about this yet, but the reason that resistance happens in a material is because the free electrons that are moved in response to a voltage or an electric field or something like that, they bump into the atoms in the solid. So the longer that the wire is, the more chance there is for these things to bump into atoms. So there's little collisions, is basically what it is. And the area, I guess if I was giving a really simple one, if I said that kind of the reason that resistance is a thing in the first place is because electrons can bump into things in the material it's traveling in. If you have a bigger area A, you'll have a lower resistance because I guess a very simplified way of thinking about it is there is more, if you have more space here, you can dodge to get around the obstacles in the wire, that kind of thing. So that's kind of the way to think about each of the individual parts. Um, I I think the fact that you guys may have not um, seen this is just I'm like one lecture, half a lecture ahead in putting this together. So if you guys are still talking about resistors like tomorrow class, that kind of thing, I'd be very surprised if you didn't see them. Um, it would be totally shocking if you guys didn't get this eventually in the notes. So it might just be a slight mismatch in timing and scheduling. So Coleman had a question that I think I can work into what we're currently talking about. So is the equation that we use down below specific to um, an ionic equation? No, this is kind of specific to anything that has a resistance here. Kind of what we call ohmic resistance, or its normal. So something that's ohmic, it also means that it follows Ohm's law, that V is equal to IR, that kind of thing. So what we're doing, this applies to anything that you could call ohmic. It applies to most resistors. Pretty much any resistor you're going to see in this course, you can assume it follows this equation, both Ohm's law and the equation that we've been using for resistivity. The assumption that I kind of just glossed over, didn't even mention it really. In this case, we assumed that the solution, which has all the ions and stuff like that, is ohmic. So we assume that it follows V equals IR. We assume that it follows resistance equal to resistivity times area divided by, or times length divided by area. Now that I'm looking at this, I think I actually made a mistake, so I'm glad we were still chatting about it. I got my terms backwards on this one. So I just need to flip these everywhere. If you reference what we had on the previous slide, that was correct. And it also follows the logic. The longer the wire is, or the path for the current to go, the more resistance. So I just need to change these. Okay, cool. I'm glad we caught that. Yeah, so I think maybe I'll just go poking while we're still all here. I don't think I haven't really